Hey guys, here we meet with the last lab, force on a rotating system. This is actually pretty similar to what you see in your lab manual. You can actually compare the background and the theory in the lab manual with this document. This is actually a little bit simplified compared to what you had to do in the lab. Okay, so the purpose is finding the moment of inertia graphically and using equations. So I'm gonna skip the equations here. You can go over them, take your time and go over them. And this is the link that we are using this time to run our simulations. And the video, after I record this, I will include the link and send this document to your TAs. Okay. So I'm going to click on the video, and I actually have read all what I had to read down here. But before you guys click on the link, please read what you have down over here, and then you can actually go there and check it out. So if the link doesn't work, of course, you can cut it and paste it on any web browser that you like. And once you do that, this is what actually happens. Okay, so you will be led to this page which says rotational inertia and torque. So here the default values set in this is a radius at 1 meters, and mass 2 kilograms, and force at 10 newtons. And as you know, torque is R cross F. So the radius is 1 meter and the force is 10, and this is where the external force is applied, and this is the center of rotation. And R value, and I mean R, which is the direction, and the angle between them is 90. R cross F expands to RF sine theta, in this case sine 90. Sine 90 becomes 1, so it is basically R and F. So R is 1, F is 10, and the torque is given to you as 10 Newton meter. So solid sphere is what we are using. It is actually checked as the default solid sphere. So once all the numbers, all the values are set here, you can click on the start run. You can click on the start button, and then you can see that the sphere is rotating around the axle, around the central point over here through this through the axis. And the torque is 10 Newton meter, and the alpha, this actually is alpha, not a, angular acceleration is 12.5 radian per second square. So when this appears, you can click on the pause button, and you can write down the torque value as well as the angular acceleration values. Okay, so the next is to set the values to different numbers. Those are given to you. So the radius you can set as given in the document 2.5, and mass you can leave it as 2 kilograms, and the force you can start with 5 newtons. And once you set all those things, you can actually click on reset. None of them actually change, and then you can again click on the start button, write down the torque value, and wait until the angular acceleration appears on the screen to pause. Okay, I think it's pretty straightforward. You are repeating this experiment for 5 force values, and then you're basically done. You go back to the document, and here you have a table, and the force values are changed from 5 to 25 in 5 Newton increments, and the torque and angular accelerations, those are given in the simulation, so you record them. And what you have to do is plotting a graph, torque versus angular acceleration. And when you do that, you actually can use this equation, torque versus angular acceleration, y-axis torque, angular acceleration in x-axis. Once you plot this graph, it will look like a y equals mx type, and using that, using the slope, you will be able to calculate the moment of inertia. Once the moment of inertia is found graphically, you can also use 2/5 mr square, 2/5 mr square equation to calculate the moment of inertia of a solid sphere. We actually picked the solid sphere in the simulation. So compare the two answers. I hope they'll come close. because some of the simulations that we are using are not done by us, and the reference is given to the website that I am copying the simulation. Okay guys, so wish you all the best with this report too. And this is sort of the end of the last this is the last lab for this semester.